Today we're going to be looking at connected particles. So we've been looking at particles by themselves, and now we're going to look at what happens when we connect them together with different things. So what we're going to look at is we're going to look at Newton's third law, and then look at how we can solve problems using Newton's third law with objects connected via rods or particles connected via strings. So what is Newton's third law, you might ask? Go ahead, give yourself a minute to think about it. So Newton's third law is each force has an equal and opposite reaction, right? That's what allows us to walk. As we push down on the ground pushes back on us, right? I'm pushing my hands together. This hand pushes on this one has to push back. If it doesn't, if the forces are imbalanced, there's a movement. Okay, and we can look at systems individually or as a whole. Go back to my hands. We could look at my right hand, my left hand, or we could look at both hands together and see what happens. Okay, some of the keywords that you need to know for this section. The first being a rod. Now, a rod is anything that can be modeled as a rigid connector, meaning it can both push and pull. Okay, generally speaking, in this class, rods are assumed to be massless, or their mass is negligible. Right? Remember, we learned about the word negligible, meaning if the mass is so small compared to the rest of the system that we can ignore it. Other things we're going to look at are tension and thrust. Tension and thrust are opposites of each other, just like acceleration and deceleration. So tension is an inward pulling force, pulling two objects together. Now, might be counterintuitive to you, because we're used to, as we pull on something, right, that we're pulling it apart. So we might think tension is a pulling apart. Well, pulling apart is what we're doing externally, right? If we put on our Magic School Bus force goggles and could see what's happening inside, what's happening inside is there's tension pulling in, trying to pull everything together, right? That's being under tension. Right? Thrust is a pushing outward force, right? So thrust it's trying to separate two things. So think about compression, right? I take an object and I try to squish it, right? I am putting compression on the object, but the object has a thrust force because its equal and opposite reaction is trying to stop it from crushing. So hopefully that makes a little sense. It's all about how you're looking at it. Are you looking internally, right? Do you have your Magic School Bus special vision glasses on? Or are you looking at it externally, what's happening to an object? Okay. The key thing that makes connected particles 100% possible is that when they are connected, they share common acceleration, right? If a truck is attached to its trailer, they're going to accelerate at the same amount, right? If they're not accelerating at the same amount, something has gone wrong. So that's how, the only way we can solve these type of problems is them being connected and the knowledge that that means they have the same acceleration. Okay, so let's take a look at our first example here. I've got it drawn out in the notes so we can go ahead and take a look at it. Okay, so we have a car, denoted by C, pulling a trailer, denoted by T. Okay, they're driving along a horizontal surface. Okay, the driver then applies the brakes of 100 newtons. Okay, we're assuming that the trailer doesn't have any brakes. I know most of the time they do, but that's not part of this problem. Right, the car has an air resistance or a driving resistance of 80 newtons, and the trailer has a resistance of 20 newtons. So that's what we have. And they've asked us to find the tension in the tow bar, right? The tension in what is connecting these things together. So the first thing we need to do is we need to do what we always do, draw a force diagram. And we're going to draw two of them, okay? We're going to draw the trailer first. So it's going to have some tension force that way because we're going to cut the diagram here, okay? And then we have some resistive force this way. So this is 20 newtons. Then we're going to cut here for our other force diagram, our C. And we're going to have three forces, right? Some T, some 80, and some 100. Now we can start to solve the problems. So let's write this one out. So sum of forces in the x direction, mass times acceleration, equal to negative t minus 80 minus 100. Now we know the mass of the car from the problem. They give us the mass of the car as 1,500 kilograms. So 1,500 times A equals negative t minus 180. Okay, so as far as we can go, because we don't know t or A, so let's go to the other one. So we can look at the trailer. So sum of forces in the x direction, mass times acceleration, and that's equal to t minus 20. We know the mass of the trailer. The mass of the trailer was given as 500 kilograms. So 500A equals t minus 20. So now we have two equations with two unknowns, and we can substitute and solve, right? Because we know this A and this A are the same. So if you wanted to, you could substitute them in. Just what I'm going to do. So we can say that A is t minus 20 divided by 500. And then we can combine them. So 1,500 t minus 20 divided by 500 equals negative t minus 180. So we can simplify this a little bit. Zeros will drop out, so we're left with 15 over 5, which gives us 3. So we're left with 3t minus 60 equals negative t minus 180. So you get 4t equals 120. So t then is equal to negative 30 newtons. So there we go. We just found the tension in the tow bar. Now let's go back up and let's check that. Or no, we needed to then find. No, that's it. We could go back and find acceleration, of course, right? So so we could take this, put this back up into here, and figure it out. So let's find out. Acceleration equals negative 30 minus 20 over 500. So that's negative 50 over 500. That's negative 1 over 10 meters per second squared. So there we go. That's the first part of our example. Second part of our example, let's take a look at our next page here, is now we're going downhill. We're on a slope. It's going to be no different than when we were looking at inclined planes prior to this. The first thing you have to do is flatten it and decompose your vectors. So let's look at our t. Okay, we still have 20. We still have t, but now we have our normal force acting straight up, but gravity is acting that way. And then what color did we use for the car? Car was in purple. Okay, so then we have the car. It's the same way. Whoops, I drew G on the wrong side. Gravity goes that way. Everything else stays the same. So the only thing that changes is we have to add the components of gravity in. So we said 80, T, and 100. So we do it again. Sum of forces in the X equals mass times acceleration, which is equal to, we know it's negative T minus 180. Now we're going to add W sine theta. So we get 1500A equals negative T minus 180 plus 15,000 sine of 3. And then you can simplify it out. We go to the other one. Go to our Go to our trailer. So we've got sum of forces in the X direction, mass times acceleration, T plus 5,000 sine of 3 minus 20. So I'm going to solve this one a slightly different way, just to show you comparing systems. So this is 500A equals T plus 5,000 sine 3 minus 20. And let's look at systems of equations this time. So let's do 1500A equals negative T plus 15,000 sine 3 minus 180. Let's add the two equations this time. So you end up with 2,000A equals 0 plus, they're both the same, so they add 20,000 sine 3 minus 200. So now we can simplify this a good way because we've got 2 zeros in all of these that we can get rid of and a 2. So this is left with 10A equals 200 sine 3 minus 1. And then you get A is equal to, this shouldn't be 20, it should be that. A is going to be 10 sine 3 minus 1 over 10. Acceleration then is equal to 0.423 meters per second squared. And now that you know acceleration, you can go back up and find the tension. So you can take this, put it back into there. So 1500A, sorry, there equals negative T minus 180 plus the rest of it, and you get T to be negative 30 again. Interesting interesting. So let's take a look. In part A, we found our acceleration to be 0.1 meters per second squared. In our second part, we found our acceleration to be 4 times that amount. Wait, did I get a sign wrong? Nope, sign's not wrong. So we found in the first part that we're looking at here, we got a negative acceleration, right? Which means we're slowing down. In the second one, we're going downhill. We found that we're actually increasing in speed. But what we found is that the tension between the two remained the same. Ask yourself, why do you think that is? The tension between them remained the same because the same change happened to both objects in the system, right? They're both on the same slope, and none of the resistance changed. So the tension between them is going to remain the same. All right, let's go back to our notes. So here's an example I want you to try on your own. Answers in the book, and see what you can do. So pause here, solve this problem, ask any questions if you have them, and then come back, and we'll keep going. So what we looked at were with the trailers and the train cars were rods, things that you could push or pull with. Now we're going to look at connected with strings. So what happens? Right, so strings are kind of special in that they can change direction, right? You can put a string over a pulley or a peg. Pulley would be a wheel that spins. A peg is just something the rope or string travels over, right? String can be in only 2 states, okay? It can be under tension, right? You can be pulling with a string, or you cannot be pulling the string. It can be slack. You cannot push a string, right? You will never have a thrust force with a string, okay? Just like almost every unit in this class, there's assumptions we make, okay? We talked about one of them already, being that it's massless. The other assumption we make is smooth pulleys or pegs, right? So that means that our direction changes, but the magnitude of the force is not affected, right? In reality, we would have frictional losses from a rope changing direction. And if you were to look up the mechanical advantage of a pulley system, you would find that the mechanical advantage, say, of an ideal situation would be 2 to 1, might be 1.5 to 1, simply because of the frictional losses in the pulleys. So for this class, we're going to assume that they are smooth, unless otherwise noted. We're going to assume that they're smooth and that there are no loss of force to the pulley or the peg. Right? And so let's take a look at this example.